Protection of Information Assets, Part 4. If you think back to a few movies earlier when we looked at the 7-layer OSI model and the allegorical Fellowship of the Token Ring, we discussed the many players in the process of getting messages and data and transactions from one domain to the other, from the Queen's domain to the King's domain. What we didn't explore, however, was doing it in a secure fashion, moving messages and data and transactions over an untrusted network like the internet, or in this example, across a dangerous and vulnerable countryside. What the Queen and King need to have is assuredness that the data is going to be confidential, that no one's going to look at the message in transit. They also want to make sure that the message doesn't change between the two endpoints. Nothing's modified. And also, they want some type of origin authenticity to make sure that the king's really sending the message and the queen's really sending the message. Now, this was the Middle Ages. We would use things like royal seals on the outside of the scroll. We would also threaten the transporter with beheading or torture if they allowed the message to be compromised or stolen, or if the seal was broken, or if the message was changed. Well, we don't really use those methods anymore. What we do use, however, is a global international standard called IP security, or IPsec. So in this Nugget movie, we're going to focus exclusively on what an auditor really needs to understand, and that is to make sure that your organization has in place some type of IP security mechanism to assure that transactions and data transfers and messages sent over untrusted networks have a high degree of security, confidentiality, integrity, and authenticity. We'll start out this discussion looking at the concept of encryption. Now, the first thing we want to talk about here is the concept of encryption. And encryption is important, or cryptography, because it's going to be the foundational mechanism that we use to achieve the four critical services of IP security. And that is confidentiality, data integrity, origin authentication, and anti-replay protection. So we're going to use cryptography in one form or another to achieve these goals. Now, encryption is basically the process of converting plain text data or messages into ciphertext, or a secure coded form of text, which a malicious user cannot understand without reconverting it back into its plain text. This is the reverse process called decryption. This is accomplished using advanced mathematical functions combined with special passwords called a key. So encryption mechanisms protect data in transit, whether it be wired or wireless information. It also protects information in storage. You can encrypt data on your hard drive. You can also encrypt data in other storage areas as well. For example, Windows has what's called the encrypting file system. Encryption mitigates against structured attacks, planned attacks within or without our network, and unstructured attacks, accidental modifications, or unintentional alterations of data. As I mentioned, encryption is also used to verify data integrity and authenticity of messages or data. Encryption is essential, but it's not a complete solution. It's not foolproof. As a matter of fact, one of the most popular encryption techniques, DES, has already been cracked. Also, in many countries, cryptographic laws are enacted, so you can't just simply import and export cryptographic mechanisms from one country to another without possibly breaking laws. So from a practical standpoint, we want to focus on really three aspects of this encryption process, which is confidentiality, data integrity, and authenticity, or the origin authentication. Now, confidentiality is simply scrambling or encrypting the data or the message, whether it be an email message or a file transfer or some attachment to email, data in transit over the wire or wireless, using either one of three typical methods: DES encryption, triple DES encryption, and AES encryption. And really, as you move from DES to triple DES to AES, you get from basically strong to stronger to strongest, and they combine with their encryption algorithm key sizes, and the key is really just a password. And I'll show you an example here of that in a second, but for example, DES uses a 56-bit key size, so the password or the string of alphanumeric characters that it uses to do its thing is 56 bits. AES, however, can use much higher bit values, much larger keys. It takes more processing, but it's much more stringent. Triple DES and AES have not been cracked yet. Now, we use those for confidentiality of data. For data integrity, we use two common, what are called hashed method authentication codes, HMACs. The two common algorithms are MD5 and SHA-1. Now, the way that the algorithms work, it doesn't really matter, but I'll kind of give you an idea here of what happens when you use one of these HMACs to guarantee the integrity of data. Let's go over to a little sidebar here. Let's talk about data integrity, which is so important. First of all, I've got a message or a transaction that I want to get from point A to point B. And I want to make sure that in transit, either over the wired or wireless medium, that the integrity of the data stays intact. In other words, I don't want one bit, 1, 0, or 1 to be modified either accidentally or maliciously in transit between these two peers. So I take my original message and I combine it with a key. And let me just show you what a key looks like real quick. We'll return to this screen here in a second, but this is what a key looks like. See, it's just a string of alphanumeric characters. This happens to be 512 bits. We then take the message and the key and we put them together and run them through what's called a hash function. And a hash function is kind of like, let's say, if the message and the key represented a large bowl of marbles. If you take that large bowl of marbles and you drop it on the floor and it breaks open and the marbles go everywhere, the odds of being able to take all those marbles and putting them back into the jar is astronomically almost impossible. In other words, getting all those marbles back into the jar in the same exact position or location. This is all based on factoring extremely large prime numbers. So this hash function basically applies this, and we have two to choose from. We have HMAC MD5, which uses a 128-bit key, and again, so it's 128 bits that key's using. What I showed you earlier was 512 bits, so it'd be shorter obviously than that. Or you can use SHA-1, which uses a 168-bit key. Now, what it uses is a shared key, so both the sender and the receiver both share this key. So they both have either the same MD5 key or SHA-1 key. And there's mechanisms in place to help both of these two parties generate those shared secret keys, either by sharing them over FedEx or over the phone or encrypted email or hand delivered, or you can use a process called Diffie-Hellman to allow you to do this over a long distance. Irregardless, once the message and transaction get run through the hash algorithm, the output is going to be a hash, okay? And this hash is basically, if you see message digest here, it's kind of like Reader's Digest, a bunch of books that are digested down to a fixed length. Well, that's what happens. You get a fixed length for MD5, and again, this is just a bunch of alphanumeric characters, okay? I'll just put alphanumeric characters. That's your hash. Then what happens is the hash function gets appended to this original message. So here's our original message again. It gets appended to that message, and then it gets sent to the recipient. Now, when the recipient gets it, they take this message with the alphanumeric hash appended to it, and since they're using a shared secret key, they use that same key to decrypt the message. And then once they apply this same hash function and the same key to it, if the result is identical, then you know what? They know that integrity of the data or message is intact because not 1, 0, or 1 has been changed. And now if one bit has been modified in this entire process, then the result after applying this decryption using the same key would be different. And this person would know that it's been modified, so it would reject the message and send an error back to the sender. That's data integrity. Now there's two general categories of keys, okay? And again, keys are just strings of alphanumeric characters that are used kind of either as passwords or they're used as part of the mathematical algorithm to accomplish the goal, whatever it is, integrity, authenticity, or cryptography encryption. Now with symmetric keys, each peer, like we saw in the previous example, each peer uses the same key to encrypt and decrypt the message or data, or they'll use the same key to apply it to a hash algorithm. Either way, it's the same key. It's symmetric. DES, triple DES, and AES are popular symmetric key algorithms where both sides have the same secret key. MD5 and SHA-1 also use a shared key as well, symmetrically. Now, asymmetric is where the local end uses one key to encrypt and the remote end uses another key to decrypt. So the local end and the remote end both have what's called a key pair. Okay, they've got a pair of keys. Let me just make a little keys here. And what happens is this. Each side has what's called a public key and a private key. The private key is secret, so only they know their private key. But the public key, they make public, so that anybody they want to talk to over, let's say, an untrusted network like the global internet, if they want to allow them to get their public key, they can share that with them, and they can use this in part of what's called a public key infrastructure. Now, to make sure that these keys have integrity, and that they are who they say they are, we use a certificate authority, okay, like a company like VeriSign or Thought, someone like that. And these are combined with digital signatures. And think about it this way. If I'm going to conduct financial transactions, or I'm going to try to exchange secure messages and data over a large untrusted network like the internet, I want to be able to make sure that individual people who are who they say they are, and that systems that participate are who they say they are. So I might want them to have a passport or a driver's license of some kind so they can drive this information highway in a secure fashion. So we have these digital certificates which contain the digital signatures or digital passports of end users and end systems. Now, this public key infrastructure uses what's called typically RSA. And RSA is a company, and it's a mechanism for generating key pairs in a secure fashion. And of course, they use asymmetric key algorithms. Why? Because there's two keys, a private key and a public key. So if one party, we'll say party 1, has the public key of party 2, they can use that public key of party 2 to either encrypt or decrypt the data, depending upon who initiates the transaction. So it's a very interesting concept, but the intricacies of it go way beyond the scope of the CISA exam. Now, encryption systems have key elements, no pun intended, and there's really three encryption elements. The encryption algorithm itself, in this case the encryption algorithm that we've used on this Cisco router, we're issuing the command crypto key generate. We're using the RSA algorithm, so we're generating RSA keys. Then you have encryption keys, and of course here's the key down here, and it happens to be a 512-bit key. And this is the key link. So what we see right here in this one little configuration on this peer or one of the participants in an encryption-decryption relationship is the protocol or the encryption algorithm, RSA, the key length, 512 bits, and the actual key itself, which is a string of alphanumeric characters. This just happens to be a key that's generated for a public key infrastructure. So you've got a private key and a public key. And this information will be used to actually generate the digital signature of this device. And of course, this information can be registered with some type of certificate authority up there. And once they do, this trusted organization will now allow them to share the public key of this device with literally hundreds of thousands of users all over the internet. And then they've got these key pairs, and they can do all sorts of secure activities on the internet or within an organization for that matter. So the third concept here is that of origin authentication. If you're using a public key infrastructure, you want to make sure that the person sending the message and initiating the secure communication is who they say they are. So we use digital certificates and digital signatures to provide this capability. The two main types of digital signature encryption methodologies are RSA, which is what we use here in the public enterprise, and the government uses what's called DSA. Now, if we're generating these RSA keys like I saw earlier in that previous output on that router, how do we distribute these origin authenticity keys? Well, we can either pre-share them, and again, as I mentioned, we can pre-share them by simply generating the keys, as we saw earlier, and then literally sharing them, sending them in an encrypted email, in a FedEx, over the phone, which is not a good way to do it, hand delivered. Okay, they can pre-share them, or we can also pre-share them using a protocol called Diffie-Hellman that is specifically designed to help two parties generate pre-shared key material without actually having to come in contact with each other. It's pretty cool. Or they could use a public key infrastructure, a PKI, where both parties are relying upon a certificate authority to distribute those private and public keys, whether they're RSA or DSA. And then there's another method called encrypted nonces, but we're not really concerned with that right now. So let's suppose I want to use RSA in a public key infrastructure scenario to authenticate the origin of the message. So here's the local side over here, and here's the remote side. Now, we're using what's called a certificate authority to make all this possible. But what both sides have generated is a public key. We'll say this little blue key here is the public key, PU, and the private key, the black one here, is PR. So both sides have generated a public key and a private key. Only they know the private key, but they've used the CA up here to distribute their public key to anybody over the internet that they want to communicate with. So, how does this process work? Well, let's say that the local is maybe you sitting at home using your high-speed internet connectivity, and the remote site is, let's say, a bank, and you want to do a transaction with your bank. You want to make sure, and the bank wants to make sure, that if you're trying to deposit, let's say, $1,000 into your checking account or do a transfer from savings to checking, that the origin of this particular information is authentic. They want to make sure that you are who you say you are. Now, they're also going to want to make sure that the integrity stays intact as well. So we can use that data integrity process that we looked at earlier as well. But let's say we've got this similar scenario. I've got a message over here, which is we'll just call it a transaction. Okay? Now, first of all, realize that I've made my public key available through a certificate authority to this remote site over here. So they have my public key. I'm going to go ahead and take this transaction and I'm going to run it through a hash algorithm. We explained that. So we hash this. What we get as a result is a hash, a fixed length hash, just a string of alphanumeric characters. Then we take this hash and we use our private key and we apply an encryption algorithm on this hash, which is in our case RSA, using our private key, and the result will be an alphanumeric string of characters. We then take this alphanumeric string of characters, which is basically our hash of the transaction encrypted with our private key. We take this and we append it to the original message, the original transaction. We send it out over the internet and it gets to the remote site. Okay? When the remote site gets it, what they're going to do is they're going to strip away the hash. Okay? So we'll come over here, they strip away the hash from the message. They're going to decrypt it, but what they're going to use to decrypt it, they're using the same algorithm. Okay? They're using RSA, but they're going to decrypt it using the public key that we had already shared with them or sent to them. So they're using our public key to decrypt using the RSA algorithm, and then the result of that, if the result hash is a match, then we know that the originator of this message is authentic. And these electronic credentials that we have that are the public key from this local site, these are what we call digital signatures. So we use digital signatures for origin authentication. Now, let's kind of take the big picture here, and let's go back to our original Fellowship of the Token Ring, and let's say that the queen and the king want to have a communication with each other, but this time they want it to be done under the auspices of an IP security implementation with a virtual private network. So let's return to the Fellowship of the Token Ring as we look at the Queen and the King who want to share information, data, and messages back and forth over this untrusted, woolly, and wild wilderness. Now what happens really is this. We need to put in place some type of IP security. We've looked at the mechanisms, the general concepts here so far. What's going to happen now between the Queen's domain and the King's domain is this. They're actually going to set up, and if you know anything about the FTP protocol, for example, FTP uses two channels. It uses one channel, which is called the control channel, and the information sent over that channel is all the session-based information on how to set up the channel. Then the other channel is used to send data. Well, that's kind of what happens with IP security. We're going to have basically from the Queen to the King two security associations. One security association is going to be used for the control information, okay? And the second channel or association will be used for the actual data or message or transaction transfer. Let's say this outer one right here is going to be our control channel. What IPsec does is it operates in phases. So we'll say this control channel here is what we call phase 1. And what we have here is this kind of data channel. This is phase 2. Now, why do we need two phases? Well, think about it. Yes, we want to be able to apply encryption or authentication to data or messages or transactions that occur over an untrusted network between these two domains. But the actual process itself of setting up these secure tunnels and exchanging kind of the policies, which includes what encryption protocols are we using, what type of hashing methods are we using, how are we exchanging our keys and generating keying material? Are we going to pre-share the keys? Are we going to use a public key infrastructure? All that information, that has to be done in a secure fashion. It wouldn't do you any good if you're going to try to exchange data or messages in a secure fashion when all of the techniques and mechanisms that go into creating the secure tunnel are sent back and forth without any security. So you see the IPsec phase 1 basically sets up a secure control channel. Once the secure control channel or security association is set up, then we can now create a phase 2 tunnel to start sending our data and our messages and our transactions in a secure fashion. And this is where those three components come in that I mentioned. Before we can even start using the confidentiality aspect, okay, and encrypting our messages or encrypting our data, what we're going to do in phase 1 is we're going to use those data integrity mechanisms and the origin authentication mechanisms, the hashing and pre-shared keys or public key infrastructure to set up the secure tunnel, send that information back and forth, and then we can encrypt that information that we're sending back and forth. Then we'll do the same thing with phase 2. Once the tunnel is set up to send the data, we want to make sure that the data has integrity or the message is unchanged between the Queen and the King. So we'll apply MD5 or SHA-1. We'll also want to make sure that when the tunnel is set up that the Queen is who she says she is and the King is who he says he is. So we're going to use origin authentication there as well. And then to actually encrypt the actual data itself, we'll use DES or triple DES or AES to do that. So this is the big picture. It's not just enough to have this 7-layer OSI model for sending information over an untrusted network, but we need to have a secure method to do that. IPsec is the way we do this, and as an auditor, we don't have to understand the granularity of all the different protocols that go into IPsec and all the different choices we have. We need to understand, however, that the processes should be in place for secure communication and secure virtual private networking between all of the ingress and egress points of the domains, okay, of our corporate domain. We also may want to apply this security mechanism inside of our organization as we have client-server communications from workstations and laptops and back-end server farms or databases. So I'm just going to put DB here. Back-end server farms and databases and application and content servers. We might want to use IPsec tunneling here. We also might want to use IPsec security for management, okay? If we're going to be managing all these devices, managing servers, managing network appliances, routers, switches, firewalls, IPS appliances, we might want to manage these also in a secure fashion. So we could use IP security, and we could use these mechanisms for confidentiality, integrity, and authentication to protect the management traffic going between our management stations and all the devices that we're managing in the organization. So as an auditor, it is vital that you have kind of an umbrella understanding of these concepts. All right, great job. Well, that was part 4 of protection of information assets. We've got one more part for this section of the CISA series, and I hope this CBT Nugget was informative for you. We'll see you in part 5.